In this video, we're going to look at the definition of a limit and trying to build upon the understanding of what a limit actually tells us. And then we'll proceed on to evaluating limits from graphs and looking at some of their properties. Now, first of all, to define a limit is basically telling you what the outputs or the y values of a function are doing as your x values approach a certain value from both the right and the left-hand side. So what are the y's doing as your x values approach a certain number? Now, to expand upon that, in order to find a limit, we have to look at some one-sided properties because our x values, unless we're talking about in behavior limits, our x values can come at a defined value from either the left or the right-hand side. Now, from a notational standpoint, if I'm approaching an x value from the right-hand side or values larger than that x value, we're going to use a little plus sign here in the limit notation, right there behind the c. If we're coming from the left-hand side, whatever the x value is, which c is representing, coming from values smaller, we'd put a little minus sign up there as a superscript of that number, indicating the side we're coming at. And in order for a limit to exist, the left side and the right side must approach the exact same value. So the y values that my function is approaching as my x values come in a number from the right has to equal the same y value that my function is approaching as I come at that x value from the left. If they both equal the same thing, we can say that the limit exists. And in fact, I can say that the two-sided limit exists. And if I write my limit notation as x approaches a number and there's no indicator of a sign, this implies that we're talking about a two-sided limit here. And so we are going to work on expanding that definition of a limit. And we're going to look at a function here, x squared minus 9 over x minus 3. And we're just going to kind of work our way through. And to start with, we want to know, well, why is x minus 3 excluded from the domain of the function? Because it makes division by 0 is undefined. Now, the other thing to keep in mind is, well, graphically, if I am looking at what is going on at 3 on my graph, it looks like it has value there, but it's actually a hole. So we have a hole at x equals 3. Let's look at this table and let's say, all right, well, what is going on in the table as I approach that x value of 3 from either side? So I'm going to start typing into this table here on Desmos. And we see what's going on with the y values. They're inching their way close to 6. So I'm going to write these into my table. And so we can see that we're getting closer to 6 as x approaches 3 from the left. Now, from a limit notation standpoint, we can write that as the limit of the function of x as x approaches 3 from the left, so a little minus sign there, equals 6, because that's what the y values are getting closer to. Now, let's continue that table on, and let's look at the right-hand side to see what they're approaching. Now, if I'm working my way back to 3 from values larger to 3, I'm going from 6.5 to 6.1 to 6.01 to 6.001. And you see how it's really narrowing back to that y value of 6, which means that we could say that also equals the limit as x approaches 3 from the right-hand side for this function of x. We could go even one step farther and say, all right, now according to our definition, if the left side and the right side limits equal the same thing, we could say that that limit as x approaches 3 from both sides is equal to 6. Let's start looking at some behaviors that would indicate to us if a limit does not exist. And there's 3 common things that we would see. The first is that if my left-sided and right-sided limits don't equal each other. So the right side and the left side approach two different numbers. The second kind of common behavior is that I'll have unbounded behavior. So my graph will either be increasing or decreasing without bound. And the third common type of behavior associated with this is that my graph will be oscillating between two fixed numbers as x approaches c. So let's look at the function, the absolute value of x over x, and let's try to find the limit as x is approaching 0. So what we're going to do is we're going to use the table approach again that we just did a little earlier in the video, and I have this one, the graph already typed in to Desmos. So if we look graphically, what we have going on is we see a distinct jump. And so in fact, I'm going to go ahead and I'm going to make that graph here. And so the graph is at 1 until I get to 0, because at 0 I have a jump. Now notice what happens if I put in 0. It says undefined. So I'm trying to figure out, well, what is actually going on graphically there, and we're trying to determine what kind of discontinuity exists here. And so we saw graphically that the graph equaled 1 or -1 the whole time. And so I'm going to type in these x values, which get closer and closer to 0 by taking smaller steps each time. So I forgot my negative sign right there. And so all of these values equal -1, and all of the ones on the right-hand side equal +1. This limit here does not exist because in order to exist, the left side and the right side would have to narrow in on the same number. They don't. They just jump. And so for this example, we're going to write a little bit more other than D and E for does not exist. We're going to identify the kind of discontinuity. It's a jump discontinuity. The function 1 over x minus 1 squared. Now notice in this table that I did not provide any x values. So it's important to have the skill of finding a limit from a table because not all functions are easy to determine the limit of, and sometimes the algebra skills that you would learn a little bit later can't be applied. And so in order to find the limit, we would need to use a table approach or a graph if that was available. And so if I'm looking at trying to find the limit as x approaches 1, when I put 1 in, I get 1 divided by 0. I'm undefined here at 1. So I want to know what's going on there at 1. And what I would do is I would pick x values that get close to 1 from either side. I'm going to start from the left. So I'm going to pick a number relatively close to 1, so like 0.9. And then I would try to get its output value, 100. Okay. And then I would get closer to 1. So I'd say, all right, 0.99, 10,000. Then I'd get even closer to 1 by taking smaller steps at 0.999, 1 million. And so if I'm looking at what is happening here on the left-hand side, as we are approaching 1 from the left for our x values, so that would be the limit as x approaches 1 from values smaller than 1. This function of x, meaning my y values, are increasing without bound. So one way to describe these one-sided limits, even though they're not approaching a defined value, we can use infinity to describe the type of unbounded behavior. So if I say it equals positive infinity, that just means that my y values are increasing without bound. Now let's do the same thing for the right side of 1 to pick into my table. And so what I would do for the right side of 1, I'm going to kind of match what I did on the left-hand side. Now, from a limit standpoint, writing my one-sided limit here as x approaches 1 from the right, our function of x, your y values, are showing unbounded behavior again. So I'm going to say equals positive infinity. Now, we're going to learn a little bit more about this down the road, but this limit here does not exist because of unbounded behavior. Now, sometimes on standardized tests, you'll see these limits. If it was a multiple choice, they sometimes they would ask the does not exist would not be an answer choice. If both left and right sides show the same kind of unbounded behavior, what we can do is, even though the limit doesn't exist, we could describe that unbounded behavior, meaning I could set it equal to infinity. So if both sides are showing unbounded behavior in the positive direction, even though the limit technically doesn't exist, I can say it equals infinity. Now, graphically, what we have going on is we have vertical asymptote at 1. And so I'm going to show that here in this graph. So I got a vertical asymptote at 1. And then both left and right sides are going to do the same thing. So they're going to show unbounded behavior in the positive direction. Okay, now let's look at a third kind of behavior associated with non-existence of a limit. And we're going to look at the function of sine of 1 divided by x, and what is happening as x is approaching a value of 0. In the table that I have here, we are really only approaching 0 from one side. And I'm going to type in these radian values for x. Now I'm going to finish typing them here into Desmo so we can kind of see points plotted. So we look at these points here as they're plotted, and they just keep bouncing back and forth. They're not really narrowing in on any particular value. And so what I'm going to do is I'm going to connect these dots and actually make this graph here of sine. And we go look at the graph here. So you see my points plotted. Now it starts off nice smooth curve, and the period between the peaks is narrowing in and getting smaller and smaller and smaller as x is approaching 0. It's making the inside of that sine function become undefined. And eventually it's getting to the point where it's taking an infinite number of oscillations as it starts approaching that x value of 0. And so this here does not exist because this sine function is not approaching a single one value as x is getting closer to 0. It is just oscillating back and forth. So due to oscillating behavior. So I'm no artist here, but what's supposed to happen, you're supposed to get a very large number, in fact, an infinite number of oscillations as you start narrowing in on 0. And as you get farther away from 0, if I can stretch this graph, you can see how the spacing gets really spread out. All right, now we're going to talk about finding the limits from a graph. And so not necessarily looking at a table like we've done the last couple examples, but we're going to look at finding the limits from a graph. Now, there are two different ways we're looking at graphs. First is finding the value at a particular x value. So if I'm trying to find the function's value at x equals c, basically what you're doing is you're covering up everywhere on the left side and the right side of the graph. I'm covering it up and I'm only looking at a particular x value. So for this particular part, I'm looking at x value of 2, and I'm trying to see where is the function defined at that x value of 2. I don't care what's going on the sides of it, but at 2, where does the function exist? And I would see here for this one, it exists at 1. Now, If I'm trying to find the limit at x equals c, I'm doing the exact opposite. Basically, I'm covering up the x value at 2 in this problem. I'm covering up the x value that I'm looking at. And I want to see what is the graph doing from the left side of 2 and the right side of 2 to see what the function is approaching. So that's the difference between trying to find the function's value at an x value and trying to find the limit of the function at an x value. And so here we have a graph and a handful of limits to try to find. And so part A, we want to find the limit as x approaches 0 for f of x. So I go to x equals 0. And to find the limit, what we're trying to do is, so I'm coming up here towards my function and say, all right, here's my x value of 0. What is the graph doing from the left? So I work my way back to 0 from the left. The left side goes to 6. And what do I do from the right? The right side goes to 6 as well. Since the left and the right sides go to the same number, we can say that the limit is equal to 6. Now, I do that because this is a two-sided limit because there's no sign behind the x value. It's also important to note that the function does not have to be defined at that x value for the limit to exist. Now let's look at B. So we'll find the limit, and then as x heads towards 6, and then the minus sign right there tells me as I come from 6 from the left. So first thing I notice is at 6, the function is not defined there. That has no effect on me finding my limit. But what I'm doing is I'm looking at what is the function doing as I approach 6 from the left. So I get on the graph, and then I start tracing my way back to 6 from the left until I get there. As I'm working my way to 6, I get closer and closer and closer to y equals 4. So this left-sided limit is equal to 4. Now the third one. Limit as x approaches 2 from the left. So as I approach 2 from the left-hand side, now at 2, we see we got this break in the graph, so it's important that we get on the correct side of the curve. So that minus sign means from value smaller than 2, work your way back to it. Now work my way back to 2, and I'm getting closer and closer to 0. So part C is equal to 0. Now look at part D. The limit as x approaches negative 6. There's no sign indicator here, so I got to look at coming at 6 from both sides. Now, so I go look at my curve. My curve here, I can come at 6 from the right-hand side, and that's 0, but there is no left side over here that's given. So since I don't have a left-hand side to look at, I can't say that a two-sided limit exists because I only have one side. So we're going to say D and E here. Now let's look at part E. The limit as x approaches 1 for the function of x. All right, so we're talking about the limit. So I go to 1 and say, all right, what does the graph do as I come from the left and the right sides? As I come from the left side, I work my way towards 1. The function, the graph, goes to a y value of 3. And then I do the same thing from the right-hand side. So I get on the curve, I work my way back to 1, and it's also going to 3. So since they go to the same y value, we say that the limit is equal to 3. Now let's look at part F. So find f of 1. All right, so f of 1, we're looking for the y value at 1. So I don't care what the graph is doing. I look for the first place it's defined at. It is not defined at the hole at 1. It's defined right here at 1 at that solid circle. So f of 1 is equal to 1. Now let's go to G. Find f of 2. So I don't care what the graph is doing. At x equals 2, where is the function defined at? It's not defined there at the hole. It is defined right here at this solid circle. So for G, f of 2 is equal to 2. And lastly, we go to H. So at H, we want to find the limit as x approaches 2, and that's a two-sided limit there because it doesn't have a sign indicator. So I got to look at the left and the right-hand sides. So I'm actually going to write this out. So I'm going to find the limit as x approaches 2 from the left, which we already did, and then find the limit as x approaches 2 from the right. So as I approach 2 from the left, so here's x equals 2. I got to get on the curve from value smaller than 2, work my way back. And the left side of the curve goes towards an x value of 0. The right side of the curve, working its way back to 2, goes to a y value of 2. Since the two limits, or the two sides of the graphs, do not converge to the same point, they're in two different spots, the limit doesn't exist. It's a jump, so I'm just going to write D and E. All right, the last part of this video here is to talk about some properties of limits. And so I have a little table here, but I'm going to talk about a couple of them. So for this table, let's assume that the value of the limit as x approaches c for f is equal to some constant L, and the value of the limit as x approaches the same value of c for function g is equal to k. And we have some real numbers represented by constants of b and c. So the first property of limits is that if you're taking the limit as x approaches a number for any constant, the limit always equals that constant. For example, if I'm looking at a horizontal line like y equals 2, the limit as x approaches any number on the line of y equals 2 is going to always equal 2. Now, the second part here, the limit as x approaches c of x equals c, well, this is just a linear function, like y equals x. And so no matter what x value I put in as x is approaching towards, whatever the x value I put in for the function y equals x, I'm just going to equal whatever my x value originally was. So it seems like a complicated the right way to write that, but in terms of using properties of limits, I have to show that the limit of a constant is equal to the constant, and as x approaches c, this limit of x is going to equal whatever the x value is going towards. Now, we start adding some other properties in. So if I have the multiplication by a constant to a function, so b times f of x, I could actually rewrite that limit here. Let me zoom in. I could rewrite that limit as b times the limit as x approaches c for f of x. So I could pull the constant outside of the limit and just multiply it to whatever the limit of that particular function is, and that's what b times L is representing. Next property is if I have this sum or difference of two separate functions, we can break them apart. So if I had the limit of f plus g, I could rewrite that as the limit as x approaches c of f of x plus or minus the limit as x approaches c of g of x. So I could break it apart, find their individual limits, and then just add my answers together at the end. Same thing works for the multiplication of two functions. So if I had the limit of f times g, I could break it apart and find the limit of f as x approaches c. Get that value, and then turn around and multiply that value to whatever the limit is of g. Same thing works here for the quotient of two functions. So if I have the limit of as x approaches c for f divided by g, I could find the limit of f. I could turn around and divide that by the limit as x approaches c of g to get my answer. Now that only works provided that the limit of g does not equal 0, because it doesn't work if it's going to create something that's undefined. So if I'm trying to find the limit of a power function, what I could do is if f of x is a continuous function, and that's for another video, but I could find the limit of f and then apply my power exponent to my answer at the end. And lastly is the composition of functions. And this composition one here, it can get very tricky, especially if you're working from a graph and a table. And this is something we're going to do a little bit later, but it is very important to use one-sided limits when doing this. So that way you can ensure that the overall limits exist, because they can get a little tricky. But basically, if I'm taking the limit of a composite function, and if everything is continuous, then I could take the limit of g of x, see what that equals, and then turn around and put that into f, and then see uh, what my limit is. But the one-sided limits is key there, so that way you can ensure that the two-sided limits exist. So let's do a couple of examples with properties and limits. So I'm given here that the limit as x approaches 2 for f of x is 3, and the limit as x approaches 2 for g of x is equal to 4, and I want to evaluate these three problems. Now, I can't just jump right in and plug numbers in. I need to fully expand, so that way I see these limits verbatim before I put any numbers in. So looking here at this first one, I need to break everything apart. I can first break apart the subtraction, and our properties of limit says that if you have the subtraction of two functions, you could evaluate their individual parts or their individual limits and subtract them. So I'm going to rewrite it as the limit as x approaches 2 of 3 times f of x minus the limit as x approaches 2 of 2 times g of x. And then we have another property of limits that says if you have multiplication by constant, you could find the limit of the function and then just multiply by the constant on the outside. So I'm going to rewrite the first part as 3 times the limit as x approaches 2 of f of x minus 2 times the limit as x approaches 2 of g of x. Now we can substitute in values for those limits that were given. So the limit as x approaches 2 of f of x was 3, and the limit as x approaches 2 of g of x was 4. And then we would evaluate. So 6 minus 8, -2. So I have a quotient between f and g is being squared. So the first property I could use is that if I have a power applied to all my functions inside of my limit, I could evaluate the limit of the inside and then apply my exponent. So pull the exponent out. And then we can go one step farther and say, all right, if I have the limit of a quotient of two functions, I could find the limit of the numerator and the limit of the denominator separately, provided that the limit of the denominator is not 0. And then now I can substitute in all their values. So the limit as x approaches 2 of f of x is 3, and the limit as x approaches 2 of g of x is 4. I square the numerator and denominator is 9 over 16. Limit as x approaches 2 of f times g of x divided by 3. Well, I see the division by 3. Now, technically, that is me multiplying the product of f and g by a third, so I can pull out 1/3. So rewrite as 1/3 times the limit as x approaches 2 of f of x times g of x. And then use the property of limits that says if you have a product, you could find the limit of each function separately and then times them together. And so I get my limits separately. Now I can substitute in the given values. So 1/3 times 3 times 4. And that gives us 4.